I apologize for the inconvenience. I think we can finally start now. This now does work. Okay. So just to repeat once again, this paper was on robust parameter-free season length detection in time series, and I'm going to start out by defining what season length is in time series. If we take a look at the time series depicted on this slide, we can see that there is a pattern that repeats over and over again. I've highlighted this pattern with a red line below. It begins with a peak, followed by a trough, followed by a lower peak, and then there's another trough. To define this a bit more formally, a season is a subsequence of a time series that repeats over and over again, and it is supposed to be the longest such time sequence, subsequence. So if there is a sequence that repeats within itself a few times, then this is not the characteristic subsequence as I call it, but so the subsequence is supposed to be indivisible and repeating over and over again. And if we count the number of elements within this, we get the season length. Okay, so far so good. Why is this interesting? Why do we need season length detection? First of all, season length is an important characteristic of seasonal time series. There's no denying that. And secondly, more importantly even, many algorithms that work with seasonal time series require this as an input parameter. They don't work without that parameter. For example, seasonal and trend decomposition using LOES, data cube mining, or matrix profiles for those who attended the tutorial yesterday. Okay, fine. So we apparently do need season length detection, but why do we need a robust and parameter-free method for this, as suggested by this presentation's title? First of all, we need the robustness because time series are obviously not that simple. There are trends, noise, outliers, local shifts, and other anomalies that can make the analysis more challenging. And concerning the parameter freeness, this is a bit more subtle. So first of all, users have to, if they want to use methods that need the season length as an input, they have to determine the correct parameters for this. And even more problematic is if the user chooses an apparently correct season length and in that way influences the results of his algorithm in a way that he believes is correct, but maybe it's actually not what the data would say. So that's why it is important to have a method to detect season length and detect season length reliably and without parameters. Okay, so how do we do this? In theory, this is very simple. We normalize the data, we compute the autocorrelation. From that, we look for zeros in the autocorrelation, and 2 times the distance from one zero to the next is our season length. That's very simple. In practice, this is a bit more complicated. This is, by the way, based on the assumption that the autocorrelation has the same season length as the original time series, which is usually the case if you normalize the data properly. But now let's take a look at the practical system to actually detect season length in proper time series. So you can see here a pipeline of steps that are employed to detect season length, and the time series depicted here is raw data, so it wasn't modified yet in any way. If we take a look at this, we can somehow see sort of a seasonality. The peaks are always 12 observations apart. This is, in fact, financial data from the tourism branch, which, of course, always peaks in the more interesting times of year. Okay, if we perform the first 3 processing steps, so interpolation, filtering, and detrending of the time series, it looks like this. If we look at this, we can already much clearer see the indications of seasonality than in the time series seen before. But why did I choose to use exactly these 3 pre-processing steps? Because there are various other things you could do. Because if we compute the autocorrelation from this, we get something we can work with. When taking a look at this diagram, we can see 4 different curves. The blue one is the autocorrelation computed from the pure data. Since we are looking for zeros in the autocorrelation, we can't work with that because there's only 1 at the very end. If we look at the detrended version, that's already much better. That's the green curve. This one has very many zeros. The problem is it's still noisy, and we will detect very many false zeros because there is supposed to be exactly 2 zeros within one season. It has to go up, back down, below the curve, and back up again. So we employed a filter to remove the noise. Unfortunately, filtering, especially low-pass filtering, usually has a negative effect on the season length. The zeros we can see in the red curve are in fact a multiple of the correct result. And to deal with this, we interpolated the data before these 2 steps. And then in that way, we obtained the black curve, which is something we can in fact work with. If we now detrend the black curve again, in this diagram it's blue, we actually can start to work with the zeros. If we look at the diagram, there are a few zeros already very well detected, this one and this one. Oops. The distance here and here, those are correct results, whereas we would like to detect these seasons as well, but unfortunately this is an outlier in the autocorrelation. It should oscillate around the axis, but it does not. So we'll have to deal with this later. So if we now take a look at the distances from one zero to the next, and if we arrange them properly, we can see usually, if the pre-processing steps works, we see clusters. And this then is a classical data science problem, determining the correct cluster from these data points. And there are many ways to do this. We chose descriptive statistics, but there are hundreds of ways to solve this problem. If we take now a look at the highlighted cluster, the values range at around 600. This makes sense because we interpolated the data 100-fold, and this would give us a season length of 6. But in fact, the 0-to-0 distance is half the season length. So we multiplied with 2, and that gives us 12, which was the original season length. OK, this entire system was obviously tested with several time series. We tested against the strongest open source implementation we could find. That was the fine frequency method in the R forecast library. And we tested with a synthetic data set that was composed of time series that were supposed to be exceptionally problematic for the algorithms. But the real data is, of course, still more complex than the synthetic ones. And in both databases, the new method at least scored or displayed more robustness than the old method. Now I'm going to show you a few exemplar test cases. First of all, I want to show you 2 that did not work. So the one that you can see on the left side of the slide, it did not work because if you look below, the detrending did not manage to remove this zigzag trend from the time series. So the picture above is before detrending, the picture below is after detrending, and this obviously doesn't work. And the second time series has the problem that it has some outliers, but they occur somewhat regularly. And in that way, we detected too many zeros, and the clustering simply fails. Now, a few highlight test cases that did work. So we have some dense data. We have these are partially from the climate data set. We have one very long synthetic collective outlier. And in general, noisy data, and all of these worked. So now to discuss a few properties of the algorithm. It is resilient to noise and outliers, and it has no input parameters, which is very useful because you don't have to determine any settings a priori before data analysis. It has problems with complex trends. What I forgot to put on the slide is that the performance is also not ideal. It is OFN squared. I think I can still improve on that, or research in general. But the main strength is that this is not connected to any particular domain of data. So as long as the data is seasonal, I assume that this should work. But at least in the data sets that I chose, so from climate and finance data, this was the case. OK, so thank you for your attention.